G'day everyone, welcome to
Fantastic.
Lubrication Explained. And today, I feel like we needed to do something special for this episode. So if you are in this industry and you ever have to explain what you do and you say you're a lubrication engineer, inevitably you're going to get some funny looks. So I'm imagining like if you've ever seen the meme of The Rock with a single eyebrow up, that's the kind of look that I tend to get, and you have to explain yourself. So as a special for episode 69, I think we should kind of lean into it, right? And just embrace the memes and embrace the jokes. And today we are going to be talking all things personal lubricants. And actually, there's a huge amount of technology that goes into it. So it's one of these fields where you drill down into any kind of field, and there are experts in this field, and that's generally what I found with this podcast is pick any niche technology. There is someone for whom that is an absolute labor of love, and it's been kind of like their life's work. Now, the guest today, Neil Cunningham, who is the CEO and founder of the Centre for Industrial Rheology. And you might think, what's that got to do with personal lubrication? And we are about to find out. So, Neil, thank you so much for coming on the podcast.
Fantastic. Thanks very much, Rafe. Yeah, it's great to be here. Yeah, really interesting.
Yeah, this will be good. So we're gonna have some fun with this one. In fact, we are, as of recording this, so it's going to be a little bit. I tend to record these a little bit out of order, but it's coming up on Valentine's Day, so I think it is super appropriate that we are discussing this topic. So straight off the bat, right? Personal lubricants, obviously chemically very different from the standard lubricants that you'd find in something like a gearbox. And I should say that Neil is also familiar with the industrial side as well. So the tribology lab obviously tests all kinds of materials. What are some fundamental differences, right? You're obviously, I'm assuming that they're not going to be any crude oil based. There's no mineral / synthetic divide here. What kind of
Yeah,
stuff are we talking?
yeah. I think the main thing really is that in terms of composition, most personal lubricants tend to be water based, really. So they're aqueous, so they got some propylene glycol or some glycerine in there. You get some rheology modifiers in there to give certain textures and sensory characteristics, really. I know sensory almost certainly doesn't come into your world. I should imagine. Really. Yeah. So primarily aqueous based. You get some silicone based products as well, really. But I think the market is pushing away from those, really. So we're trying to keep it as natural
Yeah,
as
interesting.
possible.
And
Really.
is there a
Yeah.
particular reason why silicon would be like? Obviously, historically they've been made from silicone. Is there a reason for that?
Yeah, it's just there's been health concerns, safety concerns in the marketplace with silicones, not just in the personal lubricant world, but in the cosmetics world, for example, for quite a while now, really. So I'm not too up on the veracity of the health concerns there, really. But the market goes where the market goes, really,
Yeah.
and it's heading more into aqueous products, really.
Okay.
Yeah.
Interesting. And I mean, the aqueous stuff, we do have some familiarity with that in our world. Obviously, there's certain niche industrial applications that require some kind of water-based product, and as we know, water is not exactly a great lubricant. So the addition of some of those modifiers is kind of what gives it its performance. Speaking of which, lubricants in our world, in the industrial world, tend to have certain flow characteristics. So what are the kind of characteristics that you'd see out of the personal lubricant world?
Yeah. So, how far do we want to get into this?
Yeah, no, please.
I mean, first of all, you've got to get the stuff out of the bottle. You need to have you've got to be able to squeeze something out of the bottle, really. So it's got to be handleable there, really. You've got to apply it. It's got to stay where it's put, and then it needs to do its job, really. So in terms of this is really where we're talking rheology primarily initially, really, and you're looking for something that's going to have. I mean, most personal lubricants are typically significantly non-Newtonian, so their viscosity will be depending on the shear conditions and the situation. They'll have some gel structure to them. that has some elasticity in there that contributes to the lubricating properties of the thing. Um, you don't want them stringy. You don't want them slimy. They are, because of the nature of the product, they're exposed to the air a lot as well, really. And you don't want them drying out and getting tacky and sticky, really. So, yeah, yeah. So there's a bunch of stuff there.
I've never asked anyone to subscribe on this channel. I'm not about to ask you to. What I am going to ask is, if you find this helpful, could you please share it with a colleague who may not know anything about the channel? I've heard feedback that it's a really good resource and a really good way to instruct people that are new to the business. So if you know someone who would benefit from watching this channel and watching these videos, please share it. Yeah. Okay, so maybe we can drill down into a couple of those. So, like, as an example, you mentioned like slimy, for example.
Yeah,
Now that, I think, is a description that people can intuit, right? Like, we all know what something feels like when it's slimy. From
yeah.
a like a physical property standpoint, what would that be related to?
Yeah, I mean, this is really interesting. And so, in addition to personal lubricants, we get involved a lot with the measurement of foods and food and drink, really. So,
Mm.
and that's another situation where you really don't want slimy. And slimy, if you think about what slimy is as a texture, a slimy is where you have the inability to. I mean, let's think about something in your mouth, for example. Imagine you have some raw egg white in your mouth. So I know, pretty horrible, but slimy is the inability of your tongue to feel the texture of your palate there. So it's a surface separation there, and this comes obviously into your world and into the tribological world, really. So if you get something if you have a material that separates surfaces so much that you cannot pick up the texture and you cannot feel the roughness and the asperities, really, but you also have a lot of lubricity, so a low viscosity, then that's the slimy sensation. So uh, so when you're getting into dialing up a specific texture, you're going to want to get just the right amount of slimy in there. Really, you've got just the right amount of surface separation there, because you don't want a complete loss of feeling there, whether it's personal lubricants or something that's going in your mouth or whatever. Really, um, but equally, you don't want to go over the top. Really, so yeah,
Yeah,
does
interesting.
that?
So
Yeah,
that's kind of like a really, I find it fascinating to see how, like, actual physical properties sort of translate into something that we can feel, for want of a better word. And then you also mentioned the non-Newtonian properties, right? So I think,
yeah,
when most people think of it, they think of either shear thinning or shear thickening fluids. So,
yeah,
yeah, like, I don't know, the standard examples that are given are things like toothpaste and the, oobleck, which is that combination of
yeah.
cornstarch and water. So what property are we looking for in personal lubricants?
Yeah, so typically, in terms of the rheology, um, what we're usually looking for there is, as I say, a certain amount of non-Newtonian behavior so that you can just handle it. You can get it in your hand, so first of all, really, and keep it there. So until you need to apply it somewhere. And yeah, so a degree of non-Newtonian shear thinning, really. So, but then that has to be just right, really. So I can certainly tell you we've had a number of very interesting conversations regarding shear fields and shear rate conditions and these kind of things. But yeah, a degree of non-Newtonian basically looks after the handling side of things.
Yeah, that's really interesting. Okay, so now we've got kind of like the rough physical properties of what's
Yeah,
required out of, like, one of these personal lubricants. Um,
yeah,
how, maybe you can give us a feel for, like, how much do these need to be dialed in by the companies? Because in in my conception, say for example, in the industrial world, the reason why we're moving lubricant technology forward is often because there are changes to the machine design, or there are changes to things like the surface texture or surface roughness of the way that gears are manufactured. Um,
yeah,
People, I mean, there's evolution, but evolution's a pretty slow process. People are people, and they've been having sex for hundreds of thousands of years. That
yeah.
aspect doesn't seem to have changed much. So where is the sort of like the development in terms of these
Yeah.
these lubricants?
Yeah, yeah. So there's a few things there that are driving it really. So there is um, we've got an aging population. So an aging brings dryness with it, and so that's a big growth market for the personal lubricant world there really. So. Um, but you've also got just straightforward sort of sensory properties. Getting those right, as I mentioned, stickiness and drying is a downside really. So a lot of lubricant manufacturers are looking for formulations that can maintain a silky smooth feel for a long period of time really. Yeah, you're looking for something that's going to last a while really.
Mm.
So you don't have to keep slapping more on really. So
So
yeah,
in when you're talking about that drying out, so with the water-based
yeah,
lubricants, that's presumably the water, you know,
yeah,
disappearing, whether it's absorbed into the body or you know what have you. And so
yeah,
what is left is some of those rheology modifying. I guess that
yeah,
in a lot of cases there might be polymers or something like that, which gives it sort of like that really tacky kind of
yeah,
feel to it. Could you please just explain? Because we often use the word tackiness, but I get the feeling that
yeah,
some people are not really like. Again, it's one of those things that they could probably sense when something is tacky, but don't have a
yeah,
good definition for what tackiness is. Would you mind
yeah.
just like explaining what it is?
Yes, I mean tacky comes into all kinds of like personal care products and cosmetics and things like sun care products and anything you spread on your skin really. So in tacky, we're talking about adhesion. We're talking about two surfaces coming together, and then there's an adhesion there, and as you're pulling away, it's that force as you're pulling away there really. So we typically measure tackiness with we'll use a thing called a texture analyzer, which will be, two surfaces. You'll coat one of the surfaces in the lubricant or whatever product it is. Um, bring an upper surface, an upper probe down into contact with that under a defined force, and then you'll pull away and you'll measure the peak pull off force. And very often you also measure the area under the force distance curve, and that'll give you a work of adhesion measurement there.
Yeah,
Yeah,
interesting.
yeah,
Okay, and I can imagine why in like this scenario why that would be like an undesirable property. So another thing
yeah,
that which would be kind of helpful to talk about as well is almost like the temperature performance, right? So
yeah,
in industrial applications, we're often having to manage a very wide temperature window, whether it's stuff in being used in kilns or sort of like the steel manufacturing industry. Now we're getting up into sort of the hundreds of degrees, right down to sort of like Arctic conditions, wind turbines in Antarctic bases where you might be exposed to -50. Presumably, with personal lubricants, it's pretty narrow window, right?
it is. It's a very narrow window, really. So you'll probably take the products off the shelf and it'll be maybe sat at 20, 25 degrees, something like that Celsius there. Skin temperature is about 32 degrees. Internal temperature is 37 degrees, really. So unless there's some real action going on, you're not going to rise much above that,
Yeah.
really. So yeah, yeah. So fortunately, that's a great thing, really. You don't need to worry about the viscosity index for these things too much, really. And cold cranking is not an issue, really. So yeah.
Yeah, yeah, that's so interesting. So, and is there such a thing? Like, we obviously have our viscosity grades, right? So, your ISO viscosity grades or things like. Is there an equivalent, like in the lubricants world?
There isn't really,
Okay.
no, and there's no standard.
Yeah,
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 yeah, and that's the good thing about my world really here is there's far fewer standards really for that. So, but I do think having the SAE grades would be quite an interesting
yeah,
little
yeah,
feature on the,
yeah,
the
yeah.
zero W.
I think that's a great branding opportunity for one of the brands to say
Yeah,
like, this is
absolutely.
a 15W
Yeah,
40
yeah.
lubricant. And actually on that, kind of what if you had to kind of say, approximately what is the viscosity of one of these? Like if you were to measure it, say, do you have any idea of roughly where it would be?
Now you've got me. I mean, at low shear, you're probably going to be talking of the order of a few Pascal seconds,
Okay.
really. So yeah, yeah,
Yeah. So
yeah. But then the high share, that's going to drop down significantly. Really, that's probably going to drop by maybe a factor of 100 or so. Yeah,
yeah. Okay. Interesting. That's
yeah.
interesting. So very affected by the sheer performance then.
Yeah, absolutely. Yeah,
Yeah.
yeah. And the other thing to bear in mind there is you've got a bunch of other stuff going on, and that viscosity is going to be changing as it's drying.
Mm.
It's going to be changing, but you've also got bodily fluids getting involved as well there, really. So there's going to be interactions there. There's a whole world that we get involved with that's known as mucoadhesion, really, and this is where you get uh, a lot of products, a lot of polymer related products, for example, will be adhesive and they'll form a synergistic gel with mucin and mucus. So in your body, you've got a whole bunch of mucous membranes in your body, whether it's your eyes, in your nose, or in the vagina. And there you're going to have a whole there are a lot of situations where you may want or you may not want these sort of mucoadhesive interactions going on there, really. And some of that is dialed in, not so a little bit in the personal care, in the personal lubricant world, but certainly more in the pharmaceutical and medical devices world,
Mm.
really, where maybe you want a cough sweet or something that's going to stay and coat the throat. So yeah,
So that kind of thing fascinates me because
yeah,
let's say, for example, in a test environment like you're doing, right, where you're trying, you need something that's extremely repeatable, right? You need to be able to, so that you can dial in the properties. You need a very repeatable test, which presumably means that you have some kind of synthetic mucus that you're able to add to these tests.
yeah,
Is that correct?
yeah. Yeah, there is. I mean, the standard that's used in our world is actually it's porcine gastric mucin. So, so it's pig stomach mucin, basically.
Right.
So, and that's yeah, and that's readily available. And we'll use that for a whole bunch of different things. Really, we'll take we'll make up a solution of that, and we'll measure the rheology of that, and then we'll measure the rheology of the product that we're working with, and then you combine the two, and you look to see if there's an unexpected increase in either the viscosity or what we call the elastic modulus, the measure of the gel structure in there, really. And if you get these sort of unexpected increase, that's a good indication that you've got this synergistic interaction and this mucoadhesive thing going on.
Yeah,
Yeah,
that's fascinating. Okay, so
that's
um,
yeah,
so one thing you mentioned was that sort of like concept of viscoelasticity.
yeah.
Could you please elaborate a little bit on what that is? Because I think that's not really a concept that we encounter so much in the industrial world.
Yeah, certainly. So I think a really good example of it is you imagine you've got something like that like the hand soaps
Yep.
or the pumpable product there. So there you've got a really good example of a viscoelastic liquid. There you've got something that will if you tip it up, it will pour like honey. Really, so it's acting like a liquid, but you can also wobble it, and it's got some bounce and some gel structure to it. Really, and so you're getting this product that, depending on what you're doing to it, is either behaving more like a liquid when it's moving slowly, for example, or if you're wobbling it, it's you're pushing it into an elastic response there, really. So that specific version of viscoelasticity is what we call a timescale dependent viscoelastic response there. And whenever you have any kind of linear polymer or maybe a linear micellar structure forming in a product, then you can get that kind of behavior there. And so that's what gives you a lot of the sort of the viscoelastic handling properties of a lot of these products. Um, One interesting thing where that does also play out is that when you have these linear polymers in solution there, you're going to get an extensional behavior. You're going to get that stringing, and that also contributes to the slimy feel there, really. So, and that stringing there, when you get this, something that can form into a filament here, that then does give you that contributes to the surface separation that I was talking about. So if you could think about a really good example is you crack an egg and you have the egg hanging there, the snotty point, so to speak, really.
Yeah.
So you got that. That's called elastic strain hardening. And the egg just hangs there and it will slowly extend. So you've got this extensional resistance there. Now that's a uniaxial extensional resistance, just on the one axis. But when you've got a squeeze flow situation, you've got two surfaces that are coming together. Uh, then you've then got a biaxial extensional behavior going on. So you've got this what's called planar extension or biaxial extension there. If you've got a product that resists that that extension, like the egg white, that's also going to resist these surfaces coming together. You know, when you crack an egg in a bowl and you get a little bit of the egg shell in the bowl,
Yes.
and you try and get your finger in to fish it out, you can't get hold of it.
Yeah.
And that's a classic surface separation situation that's brought on by the rheology. So it's not a tribological situation yet. There's not that high speed movement going on there, or the hydrodynamic lift going on there. You've got pure rheology that's holding these surfaces apart. There, you've got this viscoelastic cushion there, and so that same effect, that surface separation effect, that's the thing that we get that gives you the sensory properties of a personal lubricant, or it can give you the just the right mouthfeel with if you're making a low fat mayonnaise and that kind of thing. Really, yeah.
Yeah, that is that's so interesting. Okay, so all right, so I'm always trying to kind of anytime
Yeah,
I'm always trying to sort of do a read across almost to the industrial world, right?
yeah,
So we've talked a little bit about the differences in composition, temperature, all that sort of stuff. I'm just trying to think of like what is the equivalent in terms of a mechanical system to the kind of thing that the personal lubricants would have to measure up to.
yeah.
And I mean, it's basically. I mean, I'm imagining, for want of a better word, kind of like an engine piston, right? So it's
Yeah,
like, and whenever I'm describing the relationship between, let's say, for example, piston rings and and the liner,
yeah,
you're sort of saying, well, that's actually linear motion, so it would be actually similar to a linear guide, maybe.
yeah,
And now we're
yeah,
getting almost into the realm of, well, I mean, there's some metalworking fluids which are sort of that water base, but also have to be able to provide protection against that linear motion.
okay,
Um,
yeah,
so
yeah.
is that but basically like the equivalent mechanical system that you're working with?
I think it is. Yeah, yeah. I mean, there's not a lot of rotation going on there.
Yeah,
So,
unless you're a
it's
particularly
going to
skilled practitioner.
so yeah, I mean, I'd say it's essentially it's a linear bearing, isn't it? Really?
Yeah.
So yeah, yeah, and I mean, I think the piston ring thing is a yeah, you're bang on there, really.
So
Yeah,
when you're doing like testing, for example, in the lab, is that the
yeah,
kind of setup that you are basically applying to it?
yeah. We don't use any kind of reciprocating thing, despite the fact that it is reciprocating motion typically. So we're typically using rotational. So
Mm,
we have a like, custom built kit that we put onto a rheometer. So we use a rheometer as the base unit. We'll have a compliant lower surface, so typically a silicone or a latex or a soft surface that simulates the skin, and um, and then we'll have a three-ball upper measuring system. So we're typically using three glass balls for that upper rotational system. So it's a three balls on plate geometry essentially there, really.
okay.
Bring those into contact, lubricate the surface with the product you're testing, bring those into contact under a defined load, and then we'll go through a range of sliding speeds and we'll generate a Stravic from that.
Yeah. Okay. Yeah, that's interesting. So that's not really something that I had really thought about up until now. You're right. When you said you had to have a compliant lower layer
Yeah,
because you'll get I mean, the materials that we're working with are a lot softer than than
yeah,
steel. So you
yeah,
would have situations where the material does
yeah,
like kind of deform actually under load as well, right?
yeah, absolutely. Yeah, yeah,
Oh,
yeah. So you've got a lot of elasto-hydrodynamic deformation going on there.
yeah.
Yeah,
Okay, so that might actually kind of bring us into this concept of like the normal stress type
yeah,
measurements.
yeah,
So that's something that we
absolutely.
kind of talked with offline. And could you please maybe explain that concept? And if there is an analogy in the industrial world, that'd be great. But maybe it's something that's unique to you guys.
Yeah. I think this is. I mean, I think this is a really interesting area. So when we measure, if we take an elastic fluid, so we take something like a shower gel or something like that, really, we put it on a rheometer on a plate system, and we shear across a range of shear rates. Then, in addition to the stress that's resisting the flow there, we get a normal stress. We get a stress that tries to push the plates of the rheometer apart there. So it's normal to the direction of shearing there. So um, that normal stress measurement, that's something that we've been doing a lot for the personal lubricants and for anything else from sort of food products to ophthalmic lubricants for the eyes and various other products really. And there's two interesting areas there. Number one is it predicts to a certain extent the extensional behavior, which is much more difficult to measure directly. So extensional viscosity, really, but it helps predict that extensional behavior, and that can lead into the whole surface separation thing we were talking about. Um, but the other thing is that, and I've seen a couple of references to this in the mechanical lubricant world, is that normal stress can, it's proposed that normal stress can help um, uh, create a separation of surfaces, maintain a separation of surfaces without the accompanying viscosity penalty that you would get if you're just ramping up the viscosity of the lubricant.
Hmm.
Yeah. So I think that's a really interesting area. Yeah,
Yeah, that's fascinating. Okay, so there is potential application in industrial purely
yeah,
for surface separation purposes. It'd be interesting to
yeah.
see. Yeah. So what are the kind of components within a liquid that would give you that property?
Yeah. So it's typically when you have a linear polymer, and the creation of that effect is a result of it. It's effectively a recoil effect of the straightening of the polymer. Yeah.
Hmm.
Yeah. So whenever you have any kind of linear polymers in solution, also, I mentioned about the micellar things. You get what are called worm-like micelles in a lot of soap, like shower gels and these sort of things, really. And the same kind of thing there, really. So when they're sheared, they stretch, but they generate a force that's trying to push these plates apart, really. And that has a very real effect in personal lubricants and cosmetic products and skincare and all kinds of other things, really. So and as I say, I've seen a couple of references for their where they could potentially be highly relevant for industrial lubricants.
Hmm.
Yeah,
Oh, that's super interesting. So maybe if we can kind of like branch out a little bit, because
yeah,
obviously this area of like biotribology, for want of a better word, is pretty broad, right? So you would this is one of those things where you think that it's narrow, but then the more you think about it, the more broad it gets. Because
yeah,
you've already mentioned a couple, right? So let's say, for example, lubricants for your eyes. So anyone who's like,
yeah,
I mean, I'm wearing contact lenses. I'm pretty much functionally blind.
yeah,
I can't even see the eye test without them. Um, so I'm very familiar with eye drops, and you've
yeah,
got different grades, right? Because there's those sort of like gel type ones that you have to kind of
yeah,
squeeze into your eye. If your
yeah,
eyes are feeling really gritty versus just the drops. You've got
yeah,
I can imagine all sorts of stuff around skincare, right? So anything that's applied to the face or the skin needs to have certain properties. Um,
yeah.
and then you mentioned even food and drink, right? So so um, maybe if we just dive into one of those, let's say food and drink, right? I think
Okay,
that's
yeah,
probably the one
yeah,
that people are going to be most. That's
yeah,
the one that's like kind of like the universal equalizer, right?
yeah.
Everyone eats, and everyone
Agree. Yeah,
drinks. So
yeah.
what are
Uh,
the kinds of things that you might be looking at in the food and beverage world?
yeah. So right, there's a couple of really interesting areas there, really. So firstly, I mean, the anything where you're, let's say you're removing sugar or you're removing fat from a product, not so much with drink really, but removing fat from a mayonnaise or whatever. You want to replace that with some gums that will give you the same kind of mouthfeel, really. Um, but when you do that, you're really moving away from oil in a mayonnaise will enable the mayonnaise to operate very much in a boundary lubrication situation where your tongue can feel on the surface of the palate. You've got the lubrication there, but it's a very intimate contact there. As soon as you start removing the oil out of there and replacing that with gums, then you are going to get into the potentially into the into the fluid film lubrication and the hydrodynamic and the slimy sort of area there really. So that's one particular area. But another area that I think is really interesting, we talked about I talked about mucus and mucin. So in your mouth, you have it's known as the salivary pellicle. It's the layer of saliva that coats your mouth all the time. Um, and the lubricating component in your saliva is mucin. So it's a protein, it's a molecule that's present there. It's a linear molecule, and it gives you the lubricating effect, through the surface separation and these sort of things. Um, there are many products that will trash that lubrication momentarily, really. And a great example of that is something like a high tannin red wine.
Hmm.
So you have a sip of red wine, and you'll get that the dry, puckered mouthfeel
Yeah.
for a while, really. So
I've heard it described. The best description I've had of it is not a word. It's a
yeah, yeah, absolutely, yeah. So and the technical term for that is astringency. So astringency, one of the mechanisms of that astringency is it's the momentary loss of lubrication, uh, of lubricity of the saliva. And what's happening there is that certain chemicals, tannins in a wine, for example, or there are other products in maybe an espresso coffee or something, um, that are precipitating out the mucin molecules, so that they're interacting with the mucin in your saliva. They're precipitating those molecules out, and then subsequently they lose their lubricating ability. So your saliva loses its lubricating ability, and that's how you get the dry, high friction pucker mouthfeel. Really, so it's a really interesting effect, and getting that right in the food and drink industry is critical. Really, in the drinking industry, you want just the right amount of astringency, so you've got a bitter feel going on there, but not too much really. Um, in the food industry, um, a lot of plant-based proteins are famously astringent there. And so a lot of companies will be looking at formulating products that can deal with that astringency and remove those kind of effects. Yeah, yeah,
so is that becoming a bigger and bigger, let's say, component of the industry because people are looking at, let's say, for example, vegan substitutes for like because you mentioned the difference between animal fats and something like a gel. So if you
yeah,
substitute, let's say, an animal-based product for plant-based, it completely changes, let's say, the mouthfeel of and like the texture. And so the work that you're trying to do is to iterate and find something which is as close to the the feel of an animal based product. Is that
yeah. Yeah, absolutely. Yeah, yeah, yeah. So with, it could be, for example, a plant-based milk, where you may have a component in there that is bringing the astringent effect in there, really. So that needs to be dealt with in some way, really. So, and it could be looking at the oils that are present in there, really, to counteract that. So, um, and the other area there is when you're looking at sort of alternatives to animal, you're looking at, for example, meats, a major contribution to the succulence of a meat. So a burger or a juicy steak, a ribeye steak, or something like that. Really, big part of that is it's the oil in the mouth. It's the animal oil, the animal fats in your mouth, and how they're behaving, particularly as that fat is cooling down. There'll be crystallization going on and various things really. But there's a certain profile to that, really, a certain rheological profile ultimately to that. And so for companies that are looking at replacing animal fats with, for example, coconut oil, which is a commonly used one in a lot of plant-based meats, that's a real challenge, really. So because that whole temperature rheology profile is very different there.
oh okay.
It's a fascinating area. Yeah,
Yeah,
yeah.
that is fascinating. I mean, I've got a particular interest. So it just so happens. So my wife is a clinical speech pathologist, and so she
Okay.
works with cancer patients who've had mouth and throat cancer and are receiving rehab. And often because of tongue or jaw weakness, they're having to be on modified diets, and a lot
Yeah.
of her job is um, to kind of basically match the consistency of the food and drink that they can manage with whatever strength that they have left in their jaw, because if you
Yeah.
give them certain textures, they'll choke. um,
Yeah.
and
Yeah.
it's interesting because this is something that she intuits, right? She's not measuring the rheology of these products on a per patient basis,
Yeah.
but this is kind of like the underlying explanations for everything that's going on. And
I mean, and that is a really, I mean, that whole the whole area of dysphagia
yeah,
diets and foods that and uh, modifying food for somebody who has those dysphagia, the swallowing difficulties. That's a really fascinating area, really, because you've got to deal with a whole bunch of stuff there. You've got to slow the food down. I mean, your wife would know this much better than I would, really, but you've got to slow the food down so that you control it more and make sure they're not aspirating it into the lungs. Um, you've got mucoadhesion aspects to that. There could be, products could be getting stuck in parts of the mouth and parts of the throat there, really. So yeah. So it's a really fascinating area, and there is a lot of work that's going on the rheology side, and not so much on the maybe on the tribology. I don't know
mm,
to deal with that really. Yeah,
yeah,
yeah, it's great though. Yeah, yeah,
yeah. That's fascinating. Yeah, maybe we should talk offline about standardizing that kind of thing. Um,
yeah, absolutely.
Yeah,
Yeah,
yeah, that's fascinating. One last thing it would be worth kind of touching on. I mean, something that you've mentioned in the past is this idea of like the oscillatory measurements and how it relates to like wax crystallization and stuff. Could you
yeah,
please help explain um, maybe exactly what you mean by that? Because again, when we talk about wax formation in the industrial world, we're generally concerned with the pour point. So as stuff cools
yeah,
down, you get the formation of wax crystals in the oil, which
yeah.
substantially affects the viscosity behavior at low temperatures. That's primarily what we're concerned with. You're talking about a completely different mechanism.
Yeah. Yeah. So essentially, I mean, an area that we've been getting into lately with industrial lubricants, and I'm really keen for us to pursue this, is so there are a whole bunch of techniques in rheology that are known as oscillation techniques. So oscillatory testing, what you're doing, rather than shearing a material in one direction only, such as you would do with a viscometer, so if you had like a Brookfield viscometer or this kind of thing, really. So rather than doing that, what you're doing is you're gently wobbling the sample and you're measuring the resistance to the deformation, is what we call the modulus, and you're also measuring the bounce back ability. Really, you're measuring the elastic response there. So what you can do with oscillation, it's an extremely gentle technique, and you can start off with an oil that's up in a liquid condition, and you can oscillate it, and you can bring that temperature down, and as you bring that temperature down and you start to identify crystallization and the interaction of crystals, once you start getting interaction of crystals and you start getting this structure forming, the oscillation, the elasticity suddenly starts to appear there. So we're going from what we call a viscous dominant condition, more liquid than solid, into an elastic dominant condition. We start to get the formation of a network, and the network is like a three-dimensional network that has a connectedness throughout it, and that can maintain a stress. You apply a stress to it, it's going to store some energy, and it's going to bounce back again.
So just
And so it's
real
that,
briefly,
that
that
yeah,
3D structure, is that what we would refer to as gelling?
yeah,
Yeah.
absolutely,
Cool.
exactly that. Yeah, yeah. So I think the beauty of the oscillatory test is that first of all, these you've got the bounce. You're directly measuring the bounce back ability. You're directly measuring the appearance of this elastic structure in the material. Um, if you think about something like the scanning viscometer approach, you've got the viscometer running at pretty low speed, but it's still grinding its way against this structure that's trying to form as the crystallization is going on there. So it's destroying the structure you're trying to measure there. Whereas these oscillation tests are incredibly gentle. They're performed on sort of high performance rheometers that can apply super tiny little stresses and just identify the bounce back there. Really, it's a really powerful tool, and we've done some great stuff so far looking at oils and looking at wax appearance in oils and greases as well, looking at thermorheological profiling of greases. I'm really keen to explore that further, really. So yeah, I'd be happy to have a chat with anybody about that. Really, so
Yeah,
it's
definitely.
I think there's a lot of a lot of opportunity there, and it's a rapid test. It's a couple of hours test.
Yeah.
It's not something that lasts a weekend, for example.
When you say there's a lot of opportunity, so what kind of like performance dimensions are you thinking?
Yeah, well, I'm thinking that you can get a lot of nuance in the thermorheological profile. So you can identify different stages of crystal formation. You could impose, for example, certain degrees of shear at various stages throughout that. So you could see the impact of a small amount of shear on the dynamics and the kinetics of that process there. Um, and yeah, and then subsequently you could use that for sort of rapid screening of maybe additives, potential, that sort of thing, really. So aging or something. Yeah,
Yeah.
I think there's something there. I don't know but I really want to explore it.
Yeah, area of discovery. Which
Yeah,
is
absolutely.
like
Yeah,
which is how most science happens, right? Like
yeah,
it's the the age old, what do you want to call it? When people say, "Oh, that's interesting," that's usually where the cool science happens. So
yeah. Cool.
yeah, awesome. Well, hey Neil, like this was like just absolutely fascinating. I loved every minute of it. Um, you know, uh, very very on topic for both Valentine's Day, episode 69. I think just a
Yeah,
fascinating insight, and I think like for me, just so interesting to delve into a completely different area of rheology slash tribology, which is like an adjacent and connected field, but something that most of this audience doesn't really have a whole lot of exposure to. But at the
yeah.
same time, using all the same concepts, and obviously your lab still deals in the industrial world as well. No, really appreciate kind of all the insight and just having fun with the topic.
Fantastic. Oh, that's great, Rafe. We've got to keep the couples together, keep the marriages happy.
Yeah, yeah,
Yeah,
no,
I was workshopping stuff that we could talk about with ChatGPT over the last few
yeah.
days, and ChatGPT actually suggested to me that finish it off talking that you've got to talk about a happy ending.
Well, there you go. That's it. What a great way to finish with the happiest of endings. Cool. Thanks so much, Neil. Hey, I really really appreciate it.
Fantastic. That's great, Rafe. Thanks very much. Appreciate it.